Hello, and welcome to this demonstration of Arthur, a cellular automata framework written in Java. Today, I'll be showing how easy it is to produce a wide variety of unique cellular automata just by changing a few variables at the beginning of this program. Now, for those of you who aren't familiar with what a cellular automata is, it's basically an array of pixels that are either on or off. And in each frame, this program goes through and checks to see how many adjacent pixels are on and off, and then turns them on or off accordingly. Now, this is one of many rules that can be used for cellular automata, and it's the one that we'll be showcasing here. If you look at this program that I've got running on the right, you can see that it's producing quite a few interesting and varied effects using this color palette. And I want to try to break down how this is happening. See, Arthur is a little different than traditional cellular automata because he doesn't just show you what the cellular automata is doing. He shows you the changes that are taking place over time for this cellular automata. So he does this using something called linear interpolation, the same way that you can approximate a curve along control points or draw a line between two things, as is used in a lot of physics simulations. Arthur uses the same tactic to create an approximation of this change in the cellular automata over time. Now, he does this using this depth variable. And I'll go ahead and decrease this down to 4 so you can see what a much simpler version of Arthur looks like. Now this one's pretty boring, not quite as flashy as the one before it, and you can sort of guess where each of these is going. But watch what happens if I change this to 6 and then run it again. Notice how in between in each of these squares, as they're flowing outwards, they're leaving these additional lighter colors in their wake. Now, the greater the depth, the more detail we'll see in these changes as they occur. Watch, I've changed it to 8 now, so you can see that it's starting to get a little bit more complicated. And if I were to put it up as high as, let's say, 15, and then run it again, then you can see some of these very intricate patterns forming before they fade away. Now, let's move on to this variable beneath the type. Now that is deciding where the first cells are going to be spawned. Now, if you look at the bottom under here where I said to ignore, you can see the possible types, which all are codes for where the originating pixels will appear. If I choose equals and run it, then it will go along this straight line here, and you'll get a pretty interesting effect there, although it gets pretty messy pretty fast. If I change it to a minus, then it will give me a line down the center. If I change it to a plus, then it will give me a cross on either side. I can do this vertical bar, and it will just populate along this line. And I can do a circle, or O, to only spawn along the border. Now, this didn't work, and I can explain why with these next couple variables, min and range. you might remember that I said that most cellular automata function by counting the number of adjacent pixels and then using that to decide whether they will be on or off. And min and range are used to decide whether each pixel satisfies that condition. Now, min is the minimum number of pixels that have to be on next to it. So if I change this to 2, you can see that it starts to grow out at the corners in a sort of blobular fashion. And if I change it to 3 and run it again, then it will more smoothly progress forward and then fade in the center. Now, the range is the highest number of adjacent pixels that can be next to them. So currently the range says that we can only have 3 pixels before one will be turned on. But if we change the range to 1, then that means that either 3 or 4 pixels can be on adjacent. And that has sometimes a large and sometimes a small impact on the overall shape. You might notice that this is behaving quite a bit differently than before with these blobs forming in the corner, although the general structure in the center is pretty similar. And as this fills up, it will start to get more and more chaotic. Now, since the most pixels that can be on around something is 8, then if we were to change the range, if we were to make the range 8 and the minimum number of pixels 0, then it just all fills up. Now, we can do some small adjustments over time and see 7 still does about the same thing. 6 flashes a bit more and then goes away. 5, same thing. Most of these have a very, very predictable function. Even if we were to, say, change the plus, then we would still get very similar behavior across. But if we bring up the minimum range a little bit, that actually has quite a bit more of an impact on this shape. That one's pretty cool. That sort of, right at the center, it forms an interesting looking octagon. And then it all fills up and it just starts to look like noise. Now, I want to show some of the more interesting patterns that we can create with this. So I'm going to kick down the depth a little bit, put that maybe down at 6, and then I'm going to have it so only 2 adjacent pixels will turn on. You can see the edges, those are fading because the number of pixels is enough that it spawns more on the side and then fades because it goes from having 2 to having way more than 2. Let's try changing the range again. You can see already, just by changing the range from 0 to 1, we get a massively different structure, and that's part of the goal with this package, that you will be able to change some rules. Say you want it to use this equal, we'll do 1, and then we'll do a range of 2, and then run this again. And you can get some pretty interesting shapes by doing this. What's going to happen when it reaches the center? It just went away. Let's see. I'll try some more interesting ones. One of my personal favorites. Start with the plus sign. From 2 with range 5. Look at that. You can see how some of these corners are preserved. Now, what I love the most about some of these is this just looks like some kind of glowing machine. Notice how it's reached equilibrium now, and there's very little changes occurring other than some of these flashes back and forth. And that's actually one of the interesting properties about the range, or this minimum 2, range 5. And you can get some fairly similar results if you use 3 and 4. The idea is that it just has to add up to 7. Look at that. And then notice once it gets outside that range, it changes in structure. This one's a little bit more chaotic, but it will eventually settle down into this set of moving parts as it reaches the corner. But just look at the symmetry and the detail in these patterns that are being generated. Now, I'm going to talk a little bit more now about this thing right here, the lerp string. Now, normally when you do something like a Bezier curve, you would use the rows of Pascal's triangle, or the binomial coefficients, to transform. But which, in my construction, you would put 1, 1 as the lerp string. And I'll go ahead and put the depth down to 4. You can see that example. You'll notice you get 1, 2, 1. And if I change the depth to 5, then it's 1, 3, 3, 1. Because this lerp string is used to decide what this row will be. In the background, the Bez frame is constructing a triangle, and that triangle has the coefficients that will be used for transforming these. So this even works with negative numbers. If I wanted to do, let's say, 1 minus 1, and then run this same program. Actually, let's go 4 and 3 and see if that does anything cool. Uh-oh, that one just faded, so I guess I'm going to have to change that up a bit. Maybe let's try doing random. See if that gives us anything interesting. It doesn't seem to reach equilibrium, but that might be because we need to change the range a bit. There we go. You can see this fades almost entirely except for a few of these little atoms that are in equilibrium. You have the individual ones floating around. And then you've got some interesting bonds you can see on the left, and in the center are these sort of varying bonds that are alternating between a couple states. And then you have this sort of perfect bond that doesn't detach or react. And then some of these other little things floating off on their own. Let's try changing the range down to 1 and see what that does. Still fades away. Oh, now that time there was only one of these guys that reached equilibrium. So maybe let's try switching the minimum to 3. Ooh, boy. That doesn't seem like it's going to fade anytime soon. Now, what if we were to change this lerp string? Let's change it to -1, 1 and try that same construction again. Now, this is a great example of these interesting structures you can get just by changing this lerp string. Now, this behaves and looks completely different than the 1, -1 we had before. Although it's still growing into something that's pretty recognizable. What about, let's go back to 4, 2, and we'll do 1, 1 on the lerp string. Ah. You You can see that's still fading, though a little bit slower than normal. And I think we might be reaching equilibrium. You can see some similar results over here. This reaction, I like to think of these as molecules or particles floating around in this space. Now, let's change the lerp string again to -1, and run something exactly like that again. Bam! Gone almost instantly. And if we do 1, -1, not quite instantly, but it is all going away, except for, of course, these few similar ones. Now, you can use strings that are a lot longer than just 2. For example, if I wanted to use 1, 2, 3, 4, let's just do a really long one. And we'll change the minimum and range down a bit so we can maybe see some cooler looking structures. Oops. Now, the behavior of this is fairly similar to something like a lerp string of 1, 1, but in the future, these subtle variations will be really useful in finding these more unique structures. Now, this is with a range of 2, still very similar, but a bit slower and a little bit less flashy. Now, let's try to do some really cool stuff. Let's try 2, -1, -1, 1. We're going to crank the depth up to, let's say, 12, just so we can see a lot of similarities. And we'll put the cross on, and this is becoming one of my favorite ranges, 2, 5, because it produces a lot of really interesting effects over time. That has sort of a topographical effect, and like a lot of the 2, 5s with these symmetrical rates of growth, you can see that it's settling into an equilibrium. And that's just how it's going to stay. Now, what else can I show off that's of interest? No, I don't get tired of looking at that. That's pretty cool. Let's try using the period type, which will just spawn right in the center, and see how that differs. Now, if you look on the left in the console, you can see this string. That's the lerp string multiplied by itself a bunch of time and then sieved through a weird algorithm to give the string that multiplies each of the frames. Wow, that's pretty interesting. Just alternating, a little flashy. But again, you can see these really intricate patterns that form from doing this. Let's do one more. Maybe 2. I gotta stay with 2, 4. And we'll do... how about... that one's not listed in my secret ones, but... oh, I guess that one's not working right now. Oh, well, this is in the prototype stages. Now, you can see with this setup, this 2 to 5, which is, again, one of my personal favorites, it reaches equilibrium pretty much regardless of the lerp string that you use, which is kind of cool, because I can get a lot of patterns, and eventually I can use this sort of thing to procedurally generate maps or topography. I can make cool particle effects or animations. Ooh, and then once it gets to the center, that's some cool stuff. Well, it's been almost 20 minutes, so I guess I'll try to find one more really cool thing to show off. maybe 1/6. Let's see how that goes. And I'll crank up the depth some more. Throw it onto plus. And I'll just leave you with this. And then show off some more cool stuff next time. Thanks for watching.